So we saw under steady state conditions, we know that all time variables are set equal to 0. So all time varying terms, like this control volume term here, would be set equal to 0 for the steady state condition. If you have a system that's adiabatic, you would set all heat transfer terms equal to 0. And again, they don't always happen at the same time. We don't always invoke both of those assumptions together, but they're both pretty common. And in fact, what we're going to look at now are a number of very common flow devices, steady state, steady flow devices, where we're going to see those two assumptions together a lot. So in fact, we're going to say these aren't just simple flow devices. We're going to call all of these devices simple steady flow devices. So this is a conservation of energy in its most general form. As we learn how to use these tools, like the conservation of mass and the conservation of energy, I want you to write out the full, most generic, most general form of the expressions every single time. It's going to be your instinct to try and simplify these on the fly. So you simplify them as you're writing them down. And you're like, oh yeah, I'll invoke this, and I'll assume that there's just one exit and two entrances or things like that. And that type of work, once you've had a lot of experience, that's fine to use those type of methods. But for now, when you're just getting started with the introduction to these tools, it's better to be very, very careful and very, very rigorous. So we're going to use these big forms of the expressions every time as we get a feel for how these devices perform and what are some of the governing principles for the devices. Okay, so we're going to start. We're going to look at like 5 or 6 different categories of flow devices. We're going to assume every one of these devices is steady flow. So for every one of these, that's steady flow and steady state. And you say, what's the difference? Steady state addresses the time variable. Steady flow is really saying that we have steady, uniform conditions at the entrances and exits so that we can, in fact, define thermodynamic properties. If they're undefined, like if something's changing and it's unsteady flow, then I can't define a velocity or a pressure or a temperature. So these are very specific assumptions that we're going to invoke for all of these flow devices. And these are velocities, again, just to remind ourselves of the velocity terms there. So for nozzles and diffusers, these are simple systems that we'll find in a lot of flow systems. You'll find them in agriculture. You'll find them in turbo machinery, like you find in power plants. You'll find them in common household devices. You'll have nozzles and diffusers on your faucets, on your hoses, all sorts of places. So a nozzle is a contracting surface, and a diffuser is an expanding surface. So I'll draw them like this. And we always want to get into the practice of, again, identifying what the system is. So we'll draw our control volume around our nozzles. So this is my nozzle here, and this is my diffuser over here. And I always think the best example that most people understand right away for a nozzle is imagine putting your thumb over the end of a garden hose. That's a nozzle. And you think to yourself, okay, is there any work transfer in this process? So look for, mentally go through your checklist. Are there any shafts protruding into or out of the system? Do I have any electrical cords, hopefully not near water, into or out of the system? You're like, nope. You go through the checklist. Expansion or compression? No, these are rigid control volumes. So the volumes are fixed. So there's no expansion or compression work. So both my nozzles and diffusers have, by definition, no work associated with them. The other thing I want you to think about is when we consider heat transfer, you have to consider heat transfer through the system boundary. And a couple of, again, we've seen the approximation of when things are adiabatic. What does it do to the conservation of energy? Well, we've applied this simplification, the steady state simplification. When we consider the heat transfer, you have to consider things like, well, when you become more advanced in your heat transfer analysis, you'd think, okay, what are the temperature differences that we're considering? What are the mechanisms, convective, conduction, radiation? And one of the things you have to consider, the radiation is scales based on temperature to the 4th. So low temperature systems have very low radiation in general. So I'm left with conduction and convection, and some of the issues associated with those, the fundamental physics associated with convection and conduction, are the speed of the fluid. If the fluid is moving, you tend to be dominated by convection, and conduction can be neglected. And then when you look at convection, you also have to consider how long does the fluid have within the control surface to transfer heat. So imagine your body is at 98.6 degrees. Do you physically change the temperature of the water as it exits the hose? The answer is probably not. The contact exposure is so short period of time, that it's unlikely that you're changing the temperature of the fluid. So, even though your temperature is different than the temperature of the water flowing through the hose, it's not a large heat transfer rate. And that system, the nozzle system, is generally considered adiabatic. And same with the diffuser for sort of the inverse rationale. The other key properties that we need to understand about nozzles and diffusers, so the purpose of a nozzle is generally to accelerate the flow. So if we say this is the exit state here, and if this is the entrance state, so the fluid is moving like this, and the diffuser, the fluid moves like this, the entrance state, the exit state. And some of the things that we know about these systems is that, again, the purpose of a nozzle is to accelerate the flow. Well, what's the price you pay for accelerating the flow? You're going to decrease the velocity. And we know that we achieve this through changing the area of the exit and the entrance. So we know typically that we're going to see a shrinking area with a nozzle, and you're going to see an increase in the area. All of these terms will flip in their scale with the diffuser. So here we have the area is greater at the exit, the pressure is greater at the exit, but the velocity is lower at the exit. Okay, so those are the general assumptions associated with nozzles and diffusers. And again, you'll find them in numerous systems and applications. Turbines we've talked about a lot already because they are literally the workhorse of the power plants around the world. So turbines, this should be pretty straightforward for us. You'll see turbines are generally represented by this sort of trapezoidal shape. You'll see people show the flow in and out like this. Some folks prefer to show turbine flow like this. And I think this representation makes a little bit more sense. It just depends on, what your physical interpretation is of looking at these devices, these turbomachinery devices. Well, again, they all have shafts because that's how we generate work in these systems. We have the turbine blades, which are the fluid comes into the turbine, pushes on the blades, and rotates the shaft. So we know with I'll just use one of these diagrams now, that all turbines better generate work, and it's shaft work to be specific. And we would represent this as an arrow showing that the work transfer is out of the turbine. And we have the mass transfer into and the mass transfer out of the system. And if we assume, again, like we're going to do, that these are all steady state, steady flow devices, this term is going to be equal to 0. And because we actually have, let me go ahead and write down the general form of the conservation of mass expression here. In this system, just like with the nozzle and diffuser, we didn't write it down last time, there's only one inlet and one exit, and because this is a steady state, steady flow device, we know that there's only one mass transfer rate, mass flow rate in the system. So we really don't need subscripts on the entrance and exit. There is only one mass flow rate in the system. We generally approximate the turbines as being adiabatic, and I've already mentioned once before, there's actually a lot of heat transfer that happens between turbines and compressors and pumps as well. The issue is those heat transfer rates are actually very small relative to the other energy transfer rates in the system. So this is really what we should be saying. We call them adiabatic. In reality, it's negligible relative to the other energy transfers. And we're going to do an example on this shortly to show you exactly what we're talking about here in terms of the relative magnitude of the terms. If you've ever seen a turbine, they generally don't have a whole lot of vertical movement in the fluid. Some can be pretty big. They can be a story or two tall, but again, not a whole lot. So they have negligible potential energy changes. And what we're left with is essentially that the work transfer is balanced by the mass transfer. And again, because it's a controlled volume, we have enthalpy instead of internal energy. And I'm going to leave those kinetic energy terms in there. What we're going to find is that the kinetic energy, while it seems like that would be a potentially really large contribution, it actually isn't. So what we'll ultimately find is that, and we'll prove this to you here shortly, is that the work transfer for a turbine is simply governed by the mass flow rate times the enthalpy difference between the inlet and the outlet. So H in minus H exit, or H out, or whatever exit term you want to, subscript you want to use to make that notation. But it's simply a difference between the enthalpy in and the enthalpy out. So those are turbines. Compressors and pumps are the inverse to turbines. So they're just like nozzles have their mirror image in diffusers. Turbines have their mirror image in compressors and pumps. So compressors, because they are mirror images, we like to denote them using a trapezoid reflected around that axis here. And we would have, again, flow in, flow out of my turbine. We'll call this state 1, we'll call this state 2. The purpose of a compressor and a pump is exactly what the names imply. The compressor is to increase the pressure. It's actually to increase the internal energy of the fluid. And same with the pump. It's to increase the pressure or the internal energy associated with the fluid. Some folks get really rigorous about saying compressors are only associated with gases and pumps are only associated with liquids. I tend to be a little bit more flexible. I often call, pumps devices that actually compress gases. So again, I'd encourage you to be kind of flexible yourself in your interpretation of what does it mean when I call something a compressor or a pump. The purpose of the device is to increase the energy, the internal energy and enthalpy, thereby enthalpy of the fluid. So that's its purpose. And whether or not it's liquid phase or gas phase really depends on what the fluid is. Okay, so again, we're going to draw our control surface just like we did before. And if I start with a low energy fluid on one side and end up with a high energy fluid on the other side, and if it's like its sister device, the turbine, where it's adiabatic, so we're going to, again, assume adiabatic, well, then you better go through the math and say, hey, in order for that to be consistent with the conservation of energy, this has to be a system where the work is into the compressor or the pump. Okay, so we know for compressors and pumps, we're going to have work in. Also, you'll see a pump represented with this sort of a schematic type form. So you'll see, again, state 1 or the inlet state, and here's state 2. And again, be flexible on your interpretation here. So this is work into the pump. And again, these systems are considered adiabatic. So if this is the conservation of energy, invoking a few assumptions for a turbine, then we know for a pump or a compressor that it's going to have the exact same expression, except we're going to have reverse signs, okay? Because remember, we like work out in the power generation sector. We like to see work out as a positive number. This is a high energy state going into a turbine. This is a low energy state coming out of it. So this number is going to be positive. Work out is positive. For this pump, we know we're going to have the exact same governing equation, except we're going to have H in minus H out. But this term will now be negative because the high energy term is associated with the exit state and the low energy term is associated with the entrance state. And I've mentioned multiple times, we're very notation intense in this class. We like subscripts and superscripts and accents on the top of our variables, and they all have specific meaning. Having said that, I also want you to be flexible on, is it an inlet, is it an outlet, is it an exit, is it a 1 or 2? Any of those is fine. What I want you to do is just be able to recognize what's into the system and what's out of the system. So there isn't a convention or a standard convention for in, out, thing like what's the right notation. There isn't any right subscript notation except for the one that you apply, and just make sure you use it consistently, right, throughout your analysis. Okay. And that, again, we'll develop those tools through example. We'll kind of develop that habits, I should say. We will develop your good habits in how to make these notations. Okay, so the last one that I wanted to consider today, actually second to last, I apologize. There's one more I want to squeak in, is a heat exchanger. So a heat exchanger, the whole purpose of the device is to move heat transfer energy, move energy from one fluid to another by heat transfer. So the simplest way we can represent a heat transfer device or a heat exchanger is we'll just do this simple counterflow. And you're going to have flow into the system on one side and out of the system on the other. And we'll do a nice little counterflow heat exchanger here. So we have two fluids. We're not going to allow them to mix. We're going to say they can't mix in this example. And we're going to move these fluids past each other, and they're going to have conduction and convection heat transfer through the walls of the heat exchanger. So we're going to move the energy from one fluid to the other. Let's call this top fluid the hot fluid. And we're going to call this the cold fluid here. And that allows us to go, if the hot fluid is on the top and the cold fluid is on the bottom, then the heat transfer has to occur in this direction. Okay? Heat exchangers, by definition, do not require any work, so we're not going to use electrical heating or anything like that. We're going to allow these heat exchangers to exchange heat through convection and conduction. No shafts, nothing like that. So if I chose to draw the boundaries like this, the control volume around the entire heat exchanger, two key outcomes happen. One is the work transfer for that system is 0. The other thing is, and this is really important conceptually, there's no heat transfer with the ambient. That's a fundamental assumption of heat exchangers. All the heat transfer occurs between the hot and the cold fluid. So in this control volume, the system is adiabatic. And this Q is only relevant if I chose this to be my control volume. Now you would go, oh, look, there's energy transfer across that control boundary. So for this system, the blue system, the work transfer is still 0, but now I have a non-zero heat transfer. So heat exchangers require you to be thinking. Notice also in the blue control surface, I have the mass flow rate of 1 equal to the mass flow rate of 2, and I have energy transfer associated with those fluids. In the red control volume, I have mass transfer from both the hot fluid and the cold fluid. So my continuity expression, the conservation of mass, for the red control volume is actually the mass flow rate at state 1 plus the mass flow rate at state 3 has to be identically balanced by the mass flow rate at state 2 and the mass flow rate at state 4. Okay? So be careful how you choose your control surface. And whenever you look at the control surface, you have to identify all the energy transfer and all the mass transfer that cross the system boundary. If they don't cross the system boundary, they're interior. They're either completely inside the control surface or completely outside the control surface. And either way, they will not be considered. You don't have to consider those terms in your conservation equations. Okay, so remember I told you there's parallels between conservation of mass and conservation of energy. Well, let's take the conservation of energy for this system, for the red system, which includes both fluids. Well, again, there's no heat transfer across. We've assumed the heat exchanger does not have significant heat with the ambient or the environment. And we're going to have, assume that there's no work transfer. And for these systems, they're going to have negligible kinetic and potential energy changes. So these guys are going to neglect the changes in KE, kinetic energy, and potential energy for heat exchangers. Right? That's not the purpose of the device. So I look at all these simplifications. It's a steady state, steady flow. It's, no heat transfer, no work transfer. Well, heck, all I have is a simple enthalpy balance. And it has the exact same structure as the mass conservation of mass equation. Okay? So again, these are your checks and balances. If you wrote one expression for the mass, you should see an exact parallel for the energy. I want to squeeze in one last flow device onto this slide before we move on, and that's a throttle. And throttles are kind of interesting. Throttles are valves, so we'll call throttle or valves. And the purpose of a throttle or a valve is to restrict flow. So we've all turned valves many times, right? Every time you open your faucet, you're opening and closing a throttle or a valve. So we're very familiar with those devices. Schematically, we like to represent them as these little X's because, again, representing kind of the handle on my throttle. These are really funny devices. Their purpose is not to do work. Just like my nozzle, my diffuser, there's no heat transfer. The fluid really doesn't have time to change temperature as it goes through the throttle. So if I draw my little control surface here, we rapidly see, okay, well, there's no work. There's no heat transfer. Okay. We're going to, again, neglect kinetic and potential energy changes. We have one mass flow rate into and out of the system. And we look at the conservation of energy, and again, it's the same simplifications we had for the heat exchanger, except now look what happens to the conservation of energy. So we have m dot in, the mass flow rate at the entrance times the enthalpy at the entrance, equals the mass flow rate at the exit times the enthalpy at the exit, except from the conservation of mass, we know that the mass flow rates, there's just one mass flow rate in the system, so we can cancel these, and what we end up with is a constant enthalpy device. Kind of a strange little world. But throttles are isenthalpic. So there's a good word for you. So again, just a kind of a unique little simplification that happens with throttles and valves that we need to be aware of. We'll add some complexity to throttles later, but not right now. But for conservation of energy, conservation of mass, couldn't be simpler for throttles and valves. Okay, so I want to leave you with a couple of thought questions. And I want you to come up with you can either use a system example, you can think of, some actual device, or you can just think again in terms of the generic forms of the conservation of mass and conservation of energy. But I want you to answer these two questions. Can a system have unsteady mass flow and steady energy transfer? Can a system have both of those assumptions happening simultaneously, or conditions happening simultaneously? And when can you have a system which has only flow in and no flow out? So imagine a system that has one entrance but no exits.